Okay, so today is looking at cyclohexane conformations. Did you have any questions? Sure, we could do that if you want to turn them in now. Okay. All right, Okay, so let's go ahead and set this up. And for some reason, I wasn't able to find the other problems that I have, but I will write these. I will write some problems out here because that's what I'm going to ask you to do on the next exam. So I'll write some of these problems out. And then there'll be a narrated answer key, and so there'll be some of those for Monday. For the cyclohexanes that we'll talk about in a couple minutes, there will be an assignment I'll put in Canvas where there is a narrated answer key for that as well. And I reserve the right to make a take-home quiz from that stuff too. But let's do this one first. So it was 3,4-dimethyl hexane. So the first thing you have to do is you've got to draw out the structure. So 1, 2, 3, 4, 5, 6, 3, and 4. So on the front carbon, and this is the most critical part, is getting the structure correct to begin with. You have to say, okay, on carbon 3, what is attached to that carbon if it's the front carbon? There's what groups? Oh wait, we have something fun now. Thanks. Behind the red curtain, there is a giant roulette wheel. So that I can push the button and the roulette wheel will randomly call on somebody, so therefore I'm not picking on them. So I will again ask the question, what's attached to the front carbon? Give me a group. Lexi? So we got a methyl. Thanks. What else do we have? Ben? And what else? Hydrogen. So we got a methyl, ethyl, and a hydrogen. My recommendation is that you write those groups out explicitly, so that you get an idea of size. What's attached to the back carbon? Same three things. So does it matter where I put them? No. And as we're going to start learning on Monday, these two carbons can be what are called chiral carbons. And so there may be two possible answers for this because of that. All right, so here's how I drew it. So that's the first step. You got to get the groups in the right position. Okay? And again, my recommendation is don't just write CH2, write CH2, CH3. So you get a sense of how big the group is. Okay, I'll let that slide for this one, but on the exam I'm going to be a little more harsh. All right, so there's our first one. So now I'm gonna go through and I'm gonna write I'm going to go through and write then the other two staggered. So I'm going to hold the front carbon constant. Bless you. And then I'm going to rotate the back carbon. So I'm going to rotate the methyl group down here. I'm going to rotate this hydrogen up where the ethyl group is, and then the ethyl group over here. So there's conformation number 2. Do that one more time. Another 120-degree rotation. And so there are my 3 staggered conformations of 3,4-dimethyl hexane. Okay. So let's deal with those first. I'm going to erase my arrows because they're going to get in my way. Okay, now of these 3, I guess my first question would be, do any of them have the same energies? A and C have the same energies. Do we agree with that? Ben?
I feel like A would be less stable because the 2 ethyl groups are closer to 2 bigger groups.
Okay. So, but do you agree that A and C have the same energy?
And energy of stability.
Yeah.
And I thought like C would be more.
Okay, so you think C is more stable? How many people think that A and C have the same stability? Okay. I think you're being outvoted on that one, but that's okay. All right. Let's deal with that issue first. All right, remember when I set up the 3 rules, the first thing we should do is count the number of Gauss interactions. So for A and C, they each have 1, 2, 3 Gauss interactions. There's 1, 2, and 3. So they have the same number of Gauss interactions. Now we have to get to the details of looking at what group is Gauss to what. If I look at the order of this, over here I'm going methyl, methyl, ethyl, ethyl, and over here I'm going methyl, methyl, ethyl, ethyl. So since the sequence of groups is the same, their energies would be the same. If I had it switched where maybe it went methyl, ethyl, methyl, ethyl, then they would be different. So A and C have the same energy.
Can you explain why those groups are where they are, the Gauss groups? I thought they're in different places.
They can be anywhere.
Okay.
That's the thing. Depending on how you wrote your initial structure, they could be anywhere.
Okay.
So the idea is I'm just looking at the number of Gauss interactions. But when I looked at the sequence going counterclockwise, the 2 methyls are next to each other, the 2 ethyls are next to each other, and so in that case they're going to have the same energy. Okay. And they have a grand total of 3 Gauss interactions. So what about B? B has 2 Gauss interactions. And so what's going to be more stable, B or A and C? B. So the way it goes is we look at the number of Gauss interactions, and then we go into the which group is Gauss to which to break that tie. So 2 versus 3, B would be the most stable, and then A and C would have the same stability. And it doesn't matter how you showed that, as long as you indicated, A is the same as C. So then we would go to our Eclipse Confirmation. And so for our 3 eclipse conformations, what we want to do is we want to hold one of the carbons the same. I'm going to make the front carbon have exactly the same structure. Now for the back, I'm going to rotate this counterclockwise 30 or 60 degrees. So I'm going to line up the methyls, I'm going to line up the hydrogens, and I'm going to line up the ethyls. And now I'm going to do a 120 degree rotation. So the methyl group comes down here. This hydrogen goes over where the ethyl group was, and the ethyl group comes on top. One more rotation. Methyl over here, and hydrogen there. So then those would be my 3 eclipsed interactions for the structure. And in this case, this is now D, E, and F. And so rule number 1 said that numbers 1, 2, and 3 for the most stable have to come from the staggered. The less 3 stable have to come from the eclipsed. So of these, are there any of these that have the same energy? E and F? Do we agree that E and F have the same energies? So again, number of eclipsing interactions. We've got 1 eclipsing interaction there. We've got 1 eclipsing interaction there. Now we look at the specifics. It's a methyl ethyl. So same one eclipsing interaction of the same groups. And so therefore E would be equal to F. Is E and F more or less stable than D? Lexi?
No.
More stable than D? Do we agree with that? Okay. How many eclipsing interactions do we have here? 2. So that means D is the least stable. And so again, if we have a tie for the eclipsing interactions, we're going to look at the groups that are eclipsing, and the unfavorable position is going to be 2 big groups, or the bigger the group, the more unstable the eclipsing interaction. So if we had, well, we have 2 methyls and 2 ethyls, but if somewhere along the line here we had, well, we can't have it in this case, but if we did, then we would just look at the 2 groups and say, okay, is one of these groups bigger than the other? The best case scenario is always to be eclipsed to a hydrogen, or have 2 groups, and then if you have 2 large groups, that's the worst case.
Why is in the CH3 and the CH2CH3 top eclipse? Like they're next to each other?
So the thing is, there's actually 2 different answers to this problem, depending on, because there's 2 chiral centers, there's 2 answers to this problem. So if you wrote one where you didn't have this set, it's entirely possible that could happen. But in this case, when I brought this methyl group over and the ethyl group down here, that's what made them eclipse to start with. But then when I draw the other 2, I should get all the possibilities. So let me just start out with the other possibility here. So let's see, we had methyl, we had ethyl, and we had hydrogen. And then if I put my methyl group here and my ethyl group here, I might get a completely different set of answers because of the chiral center. So if you look at this molecule right here, let's draw out the staggards, and then I'll let you could draw out the eclipse. The answer key will have both. We'll have both possibilities. So again, drawing all the front carbons. Now I'm going to rotate clockwise. I'm going to rotate the ethyl group down here. I'm going to rotate the hydrogen here. I'm going to rotate the methyl there. I'm going to rotate the ethyl group up here. And then the methyl group comes down here and the hydrogen goes there. So there's three other conformations that can happen just because I switched where I put the methyl in the ethyl group. So let me ask the question here, do any of these two molecules, or any of these three, have the same energy? A and B have the same energy?
Or no, A and C.
Do A and C have the same energies? Let's do this one from scratch. All right, so how many? So we've got 1, 2, 3 eclipsing interactions for A. We've got Gauss interactions. We've got 2 for B. And then how many do we have for C? 1, 2, and 3. So A and C have 3 Gauss interactions, and B has 2. So what does that tell us then in terms of ranking these?
B is the most stable.
B is the most stable, so let's write that down. So B is going to be the most stable because it has the last number of Gauss interactions. But now let's look detailed at A and C. Okay. So if we look in detail at A and C, what do I have? I've got an ethyl methyl, a methyl methyl, and a methyl ethyl. And over here, what do I have? A methyl ethyl, an ethyl ethyl, and a methyl ethyl. And just by my description, you can't really tell if there's a difference, but let's look at the positions of the ethyl groups. In C, they're on the inside, and in A, they're on the outside. Of the 4 groups that are eclipsing, of stagger, or of Gaussing, if that's a word, the ethyl groups are on the outside in A, and they're on the inside in C. Do they have the same energies? You would think not, but let's go through and see. So what I have, let's total up the interactions that I have. In A, I'm going to start with this one. Number 1 is what kind? That's going to be an ethyl-methyl interaction. Number 2 is going to be a methyl-methyl interaction. And number 3 is going to be another ethyl-methyl interaction. So now let's come over to C. So number 1 is going to be an ethyl-methyl interaction. Number 2 here is going to be ethyl-ethyl. And number 3 is going to be what? Ethyl-methyl. So I can kind of go through here and let's see what cancels. So I've got an ethyl-methyl, ethyl-methyl, I've got another ethyl methyl, another ethyl methyl. So in these two structures, the difference is a methyl methyl versus an ethyl ethyl. And so which one of those two is the more stable situation? It's methyl methyl. So that means A is the next most stable, and then finally C is less stable than that, those two.
Does it matter which way you put like that variation for arranging like the ethyl methyl and methyl?
No, they're all going to cancel. Two of them are going to cancel out, and you're ultimately going to end up with the two ethyls on the inside. They're going to interact versus the two ethyls on the outside, right? Because over here they're only interacting with one thing and not two. So if the best case scenario would be have the two large groups on the outside, as opposed to having them on the inside. So sometimes you have to go to that level of detail. And I'll leave the Gauches, I'll leave the eclipsed ones you can draw for that one, if you didn't draw it already. So there are actually two sets of answers for this homework problem. So I'll draw up two answer keys and then see which one you answered. Does that help? Okay. All right. Well, like I said, I'll put together some more of these problems and put them online. And then you can take a look at them in between now and the next exam. And you also, if you go back and look at some of the exams ones from previous, you'll see these kinds of problems as well. I only have a limited number that I can really ask. So, okay. So cyclohexanes. So cyclohexanes are the second groups that we want to do conformational analysis on. Do we want to learn about their structure? And so, quite frankly, with a cyclohexane, if a cyclohexane was linear, this angle would be 120 degrees. That's going to be a mismatch against sp3 hybridized carbons that have a 109.5 degree angle. So if cyclohexane was completely flat, the angles wouldn't match. And what that means is that instead of having the orbitals completely head-to-head, they would be off on kind of a tangent. They'd only be partially overlapping. And that wouldn't make a nice, strong bond. Cyclohexane is the most stable of the cycloalkanes. And so something happens to this ring. And what happens to it is that it puckers. I have to say that very carefully so I don't get myself in trouble. But the ring puckers. So what does that mean? Well, here's what it doesn't mean. If that ring was completely flat, every one of those hydrogens would be eclipsing each other. Right. And when the ring's flat, the two groups would be off at an angle like that. Now, this is sometimes how you see the rings. right? Have you seen those rings, 6-membered rings written that way in biology for things like sugars? Yeah, that's not how it looks. It looks more like this. And every single one of these hydrogens would be eclipsing each other. So that's the second reason why cyclohexane is not flat. So what it does is it forms a number of different conformations. Those are listed in the book. We're only interested in one. And the one we're interested in is the one that looks like this. A chair. So this chair conformation allows the angles to relax back to 109.5. And it puts us in a position where every single hydrogen is gauche. Or if I look down any carbon-carbon bond, it's going to be in a staggered situation. Now, the biggest thing operationally in terms of drawing cyclohexanes is that we have two terms to describe them, axial and equatorial, to describe the positions, and we have to be able to determine whether the position is above or below the ring. Okay. So I'm going to erase that, and I'm going to write a, bless you, and I'm going to write a bigger one. Okay. So let's start with axial versus equatorial. Axial positions are perpendicular to the ring. Equatorial positions are roughly planar to the ring or parallel to the ring. And in the PowerPoint notes that are in the folder that my video is based off on, they're in color. We usually will do what we're going to do now in terms of drawing them for ourselves. But there are 3 axial positions up. Okay, and those are the three axial positions up, and then the 3 axial positions down look like that. So here is axial, axial, axial. I'm going to use a square to represent the positions above the ring, and then this is axial, and I'm going to use a circle to show that that axial position is below the ring. And the only reason I'm doing that is I could change colors on the screen, but unless you have like one of those 4-color pens that then are constantly clicking back and forth during a lecture, you can't colorize your notes right now. Feel free to after class when you rewrite them or rework them. Okay. So this is the easiest part, is knowing that those axial groups are above or below the plane of the ring, because they're straight up and down. Where we run into confusion is the other equatorial positions. Are they above or below the plane of the ring? We'll start with this one. Here's my equatorial position. So it's roughly in the plane of the ring. Above or below? Too late.
Lucy Kelso.
Lucy?
Below.
Below? Okay, do we agree with her? Why'd you choose below?
It's like not going straight up with the ring, but it's going towards the bottom.
Okay. Now, sometimes it's difficult to see that above or below, but can anybody else, if you think it's below, why? How did you choose? Lexi?
It's pointing away from you.
Okay, it's pointing away from you, but I'm gonna put one here. Actually, I'm gonna put one like this. So sometimes it may be more difficult to tell where the equatorials are Because, to be honest, they're all going to be kind of pointing away from you.
Because we're always in one group above or below.
There's always a group above or below, and if you can tell from the axials that you could say, oh, well, this is definitely above, that by definition makes this one below. That's what I use. Because universally, it seems everybody's able to tell the axial positions, whether above or below. So use that as your point of reference. So, for instance, what's this equatorial right here? Above or below? Above. And then what's this one? Below. And then above, and below, and above. So they alternate as you go around the ring because the axials altered, or they went back and forth. So a diagram like this, you have to be able to tell, is the group axial or equatorial, and is the group above or below the plane of the ring? So that's one of the things you'll have to master here. If you have to make a little cyclohexane ring, I don't think there's enough different colors of atoms in there to like make them all one color, but you could use like a piece of tape to indicate which ones are above, which ones are below. And in the PowerPoint, I have them color coded as well. So that's what we have to know. And why do we have to know whether the group is above or below the plane of the ring? Because cis and trans, okay, cis means that the groups are on the same side of the ring, and trans means that two groups are on opposite sides of the ring. Okay. So now we have cis and trans in a slightly different context, although they still mean the same thing. Same side, opposite side. But now I've changed the rules so that it's a cyclohexane or a cycloalkane ring versus a double bond. Okay. So, Lexi.
So how do you know which axials are above or below the ring? Is it always going to be?
It's always going to be these ones are above, and it's always going to be these ones are below. But, okay, it depends on your perspective. How do you want to look at the ring? Do you want to look at the ring from up here, looking down, or do you want to be down here, looking up? That's going to really depend on whether the group is above or below the ring. I usually look down. I usually imagine myself up here looking down. Although you can do it the opposite. And for cis or trans, it doesn't necessarily matter if it's above or below the plane of the ring. It just means, are they both above or are they both below? Or are they one of each? So that your actual perspective doesn't necessarily matter. Although most people look above the ring, including the people that wrote the book.
I was gonna say, how did you know which way the equatorial is?
Because this is the general shape. Because this is the general shape of the molecule. So when you're writing your equatorials, you want to write a bond that's roughly in the plane, but then you want that overall carbon to be tetrahedral.
Oh,
So it still has to be tetrahedral. And so you can have some funny structures that people write. I'm not going to write them right now because they're wrong, and I don't want to write any, I don't want you to say, oh, that's the way you wrote it. Yeah, I know I wrote it wrong. So there's confusion there, but it just, you have to practice drawing the positions in. like that. So one other thing. If I'm up here looking down on my cyclohexane ring, I'm going to see, I'm going to call this number 1, number 2, number 3, number 4, number 5, and number 6. So here's my numbering scheme. So if I'm looking down on it, 1 is in the upper right-hand corner, and 4 is in the lower, well, it's almost in the lower left-hand corner. So that's the way the numbering scheme would look. And bonds that are bold are going to be above, and bonds that are dashed are going to be below. So we're going to use the 2 in the plane, 1 above, 1 below, the tetrahedral representation to show groups that are above the plane of the ring and those that are below the plane of the ring. So this would be, so this diagram would be exactly what you would see looking at the ring, looking down on the ring from this position up here. So some groups are going to be bold, some groups are going to be dashed. So there's a number of things we have to be able to do with cyclohexane rings here, that we have to be able to manipulate them. Okay, everybody sort of with me? So ultimately what I'd like to do with this ring, I'd like to do a number of things with it, and we will over the next 2 weeks when we talk about stereochemistry. And cis and trans is a type of stereochemistry. We're going to look at an even more detailed kind of stereochemistry. But one of the nice things when we do that next week is I'm going to say, oh, well, we use the Kohn-Ingold pre-log sequence rules to rank not 2 groups, but to rank 4 groups, 1 to 4. And then I'm going to say, oh, you remember those from doing E and Z. And you're probably going to go, do I remember those from E and Z? But in theory, it'll only require a quick review as opposed to learning it from scratch. But I digress. So what do we want to do with cyclohexanes? Here's what I want to do. I would like to know the stability of cyclohexanes. So if I have 1 methyl cyclohexane, there's 2 different places I can put that methyl group. I could put the methyl group here in an axial position, or I could put the methyl group in an equatorial position. And basically what happens is that the ring can flip itself so that the methyl group can either be axial or equatorial. So the ring itself, if I was to bring this carbon up, I would put it into this canoe. I don't know why people didn't call this the canoe conformation instead of the boat conformation, because it would be a better description. But that boat has already sailed, and so I can't change the name. But if you bring this up, you would have the boat. The boat is a very high energy conformation. We never see it unless we do something like tie these 2 carbons together with a ring or with a carbons, and then we have a bicyclic system. And then if I bring this one down, I get what I call the left-handed chair. And the only reason I call it the left-handed chair is because I'm right-handed. So it's the opposite chair. And so if this ring flips, the axial position is still above the plane of the ring. And so when you flip the position, the axial is still above the plane of the ring, but now it's in an equatorial position. And the equatorial position is below the plane of the ring, and so now it becomes axial. So if I do a ring flip, I interchange every position on the ring. All axials become equatorial and vice versa. But this isn't bad. This isn't a bad drawing for the left-handed version, but I would like you to just be able to draw one version. So what we do is we say, oh, well, the methyl group can either be axial or equatorial. How did I get there? I did a ring flip, but I didn't write the left-hand version. So every group is going to be either axial or equatorial. Okay. So my question is, where should I put the methyl group to be most stable? Should I put it axial or should I put it equatorial? What do you think? Too late.
I shall use ale gullery.
Equatorial.
Okay. Is that what your gut tells you? Okay. Does it tell you any more than that?
It tells me that it's more stable than cyclohexanes.
Okay. Is your gut telling you that, or was the video or the book telling you that? Okay, the video is telling you that. Which is true. So, yes, you should put the alkyl group equatorial. That's where it'll be most stable. But why? Why is that? Well, it turns out that when you put a group axial, there are other groups, even the hydrogens, that are in axial positions. And so the space around the top of the ring is limited, so that this methyl group will actually be close to those hydrogens. Of course, the two hydrogens are close to each other, but something's got to go there. So having the two hydrogens in the axial position is just the status quo. So putting an alkyl group in the axial position, you're going to have these interactions. And these are called 1,3 diaxial interactions. And the 1,3 diaxial interactions are destabilizing. Even between a methyl group and a hydrogen, they're destabilizing. So every time an alkyl group or a large group, larger than hydrogen, is put in the axial position, you have a less stable conformation. All right. So it's always best to have the alkyl groups, or it's always more stable to have the alkyl groups equatorial. Now, what if I have more than one alkyl group? I could have up to 4 different energetic conformations. So how about we do this? This is one I like to have fun with. So how about we do 1, 2. And let's say I'm going to put methyl groups on the 1 and the 2 positions. So how about I put a methyl group, how about I put this methyl group axial in both cases, and then here I'll put it equatorial, and then I'll put it axial. So here's 2 different structures for 1, 2. This is 1,2 dimethyl cyclohexane. Now I have a question. I have many questions. Question number 1 is going to be, for the molecule on the left, are those methyl groups cis or trans? Cis? Do we all agree with that? That they're cis? On the left. You agree? No? You think they're trans? Okay. How many people say they're cis? That the methyl groups are cis? How many people say they're trans? How many's not voting? Why are you not voting? Okay. So, Chloe, why do you think they're trans?
The one on the left, methyl group is in the
Axial.
axial, sorry, and it's up, and then.
Okay, let's stop there. So this methyl group in the axial position, is it above or below the plane of the ring?
Okay.
Keep going.
There.
You can change your answer if you'd like.
Yeah.
So the methyl group is above the plane of the ring. Okay, so this one is above. This methyl group in the equatorial position, is it above or below the plane of the ring? It's above. So this one is also above the plane of the ring. And so that makes those two methyl groups cis. So why did I draw that diagram out with the axials and the equatorials all above or all below the plane of the ring? Because this is what we need to do. We need to look at those two methyl groups and say they're both above the plane of the ring, therefore it's cis. How about the one on the right then? What's it? It's going to be trans. Because this methyl group is now above the plane of the ring, this methyl group is now below the plane of the ring. And remember, if somebody, well, in this case, it's my experience is that people have a lot easier time seeing axials above or below the plane of the ring than equatorials. So in this case, it's axial up, it's axial down. That makes this one now trans because one's above and one's below. For the one on the left, this methyl group is above because the hydrogen is below. So there is my second confirmation. So let me quickly whip up the third and fourth, and then we'll call it a day. And we'll pick this up on Monday. So now I'm going to take that top carbon and I'm going to change the position of the methyl group to being equatorial in both cases. But now for the other one, I'm still going to have one equatorial and one axial. Now, here's what I'd like you to think about for Monday with this. Label these two cis or trans. And then take all four of those and rank them in energy from number 1 to number 4. And there may be ones that have different, that have the same energy. So they may be tied. But ultimately, this is what I'm going to ask you to do for cyclohexanes, at least initially. I'm going to give you the name of a cyclohexane, and you're going to have to draw the 4 different combinations. You're going to have to label each cis or trans, and then you're going to have to rank the energies. So for the last 2, is it cis or trans? And then for all 4 of them, rank the energies. And so what I will probably do is I'll probably put this in the Top Hat system, so when we come in on Monday, I'll get your answers to that. So you can click in the answers, so then we can talk about this. And if there's some vigorous debate that goes on over the weekend about things being cis or trans, that's natural. Because if we were to do this now, one of these would probably be 50-50. And we'd have to talk about it, but we'll instead let you work on that for Monday. And then probably on Monday, I'll give you one of these as another take-home quiz. I'll send you an email in terms of Chapter 6. I think it'll just be the reading, will just be the first couple of sections. And I will post I'll post my video for that, again, in front of those sections, so that you can watch it. You can now watch it either before or after class. It doesn't matter to me, whatever's most effective to you. So we'll do that, okay? All right, if you didn't get your exam on Wednesday, I have it, so stop up front.
There's a problem set for the Newman projections under September 5.